So for this question, I think to fully explain this concept, I'm going to draw a circuit. So we have a cell, a real cell, which we can model as an ideal cell, which has an EMF of epsilon, and a resistor in series with one another. So that would be the internal resistance of the cell, and this is then the entire cell. The entire cell is modeled as an ideal cell with an EMF of epsilon in series with some kind of resistance, which is the internal resistance of the cell, and that is R. And let's say we then attach that to some kind of, I'm going to put two components. Let's say we have a resistor and then a bulb. Okay, so there's three things I'm going to talk about. I'm going to talk about electromotive force, so EMF. I'm going to talk about terminal potential difference and then also potential difference. So EMF is defined as the energy transferred to electrical energy per unit charge by your cell or your voltage source. So from that definition itself, we can already rule out two options, because the first thing that I mentioned was energy transferred to electrical energy, which is basically work done, and it's per unit charge. And you can see that from the equation as well. Potential difference is work done per unit charge. It's not force per unit charge, and therefore it can't be A or B. So we're left with the last two options. So yeah, we have our definition for EMF now. Energy transferred to electrical energy per unit charge by your cell or voltage source. So terminal potential difference is the electrical energy transferred to other forms per unit charge in your external components. So let's put some numbers to this now. Let's say that we have an EMF of 6 volts, which is the maximum voltage that the cell can provide. And let's say if we placed a voltmeter here, then this voltmeter reads, let's say, 5 volts. So in that example that I gave, the 5 volts would be the terminal PD. It's effectively the voltage across the external components. And the 6 volts would be the maximum voltage that the cell can provide. We're not getting all of that voltage. Some of that is lost in the internal resistance, and that will be the lost volts. And then there's just potential difference in general. Potential difference is the work done per unit charge, or it's the electrical energy transferred to other forms per unit charge in any one single component. So it could be the case that across this resistor we have 3 volts, and across this resistor we therefore have 2 volts. So then the potential differences, the individual potential differences across the resistor and the bulb are 3 volts and 2 volts respectively. The terminal potential difference is across all the external components, and then the EMF is the total voltage that the cell can provide. So those last things I mentioned are not definitions, but it's how you can, a way in which you can think about what those quantities are. So we can therefore see that it won't be answer C. It wouldn't be the work done per unit charge to move a charge across a component, because that would just be the potential difference across a single component. Potential difference would be the work done per unit charge to move a charge across a single component. The EMF would be D, which is the work done per unit charge to move a charge around a circuit, and then some of that work done is transferred to the external components, and then some of that will be dissipated as heat in the internal resistance. So for every coulomb of charge that goes through our circuit, 5 joules is dissipated in the external components, and 1 joule is dissipated as heat in the internal resistance.